Okay, hello class. Um, Sorry, I can't make it to back to school on Monday. Uh, well, my ex-husband, he's a pilot for private jet, and he just had this opportunity to take us on a private jet to Pittsburgh tomorrow. And we'll get there at around 5 p.m. and I try to book tickets to come back, but there's no I can't get any ticket for tomorrow. So the earliest I can get is Monday, 7 a.m. So I'm going to fly back from Pittsburgh because yeah, because well, we are flying out of uh airport for private jet, and then I can't return a rental car, so I can't rent a car. So what I'm going to do is fly to Newark, and then from Newark take Uber to that airport to pick up my car. Yeah, so unfortunately I have to cancel the class, but I thought this is like a lifetime opportunity. And I don't think I'll be able to get on a private jet. So sorry, I have to make the class through Zoom. So I'm recording this video now. So this is our last chapter, and this is to do hypothesis tests for single populations. So last chapter, in chapter 8, we kind of talk about the confidence interval. Okay, we use the confidence interval to see how confident we are, try to estimate the average, the mean, okay? So for hypothesis test, it's very similar. So this chart, you kind of saw it last chapter as well. So when we have population mean, and when we know the population standard deviation, or when we don't know the population standard deviation, and then when we need to compare the population proportions. So there are three type of hypothesis tests, okay? So the hypothesis is the assumption for the population parameter, such as like average for or the proportion. So the population mean is the average data used for, let's say, the average data used for smartphone users is 1.8 gigabyte per month. That was, this is a long time ago. I think my daughter can use more than 1.8 gigabyte every day now. Yeah. So and then another example for population proportion will be the cell phone use with 4G contract is 0.62, okay? So 62% of the cell phone users, they actually have 4G contract. So this is an old example, but this is just to show you, those are some of the hypotheses. So for hypothesis test, we will have something we call null hypothesis and then alternative hypothesis. So null hypothesis, we would usually denote it as H0, HO. So it represent the status quo, represent like the existing relationship, okay? So in this case, the null hypothesis should be something less equal to, something equal to, or something greater equal to. So the null hypothesis always have the equal sign in there, okay? And then the alternative hypothesis is the opposite of the null hypothesis. So if in this case, let me get my pen. Okay, so in this case, when the null hypothesis, let's say null hypothesis, I use the is x less equal to 10. Okay, so x less equal to 10. That's a null hypothesis. And then the alternative will be x greater than 10. Okay, so it always be opposite of the null hypothesis. So it usually we would try to see whether or not the alternative hypothesis is true. But we want to test when it's true, we are not going to say, oh, this is true, but we are going to say, okay, the null hypothesis is not true. Okay, so we have to reject the null hypothesis to say, well, we think the alternative hypothesis is true. Okay, so alternative hypothesis is always states the population parameter is greater, less, unequal, or less than some specific number. So it's totally opposite of this. Okay, the null hypothesis. So the purpose of the hypothesis is to draw the conclusion about some unknown parameters. Like we want to say, usually when people watch more than 2 hours of TV, their GPA is lower than 3.5. Okay, then we want to use alternative to be the opposite. That's something we want to claim, something new findings that we want to support. Okay, so the alternative hypothesis usually known as the research hypothesis. So it means, well, usually people watch more than 2 hours of TV, GPA will be higher than 3.5. But then we found, oh no, people watch less than 2 hours. But then we say, well, we found out when people watch more than 2 hours of TV, the GPA is higher. Okay, so then we have to test that it's not true that when people watch less than 2 hours of TV, their GPA will be higher than 3.5. Okay, so the null hypothesis will be dependent on the nature of the test, and then the motivation of how we want to do it. Okay, so like the first example is, look at this. So the null hypothesis is the population mean that's equal to 1.8, and then the alternative will be mu greater than 1.8. Okay, so that means that someone they think the data use has gone up. Okay, so the alternative hypothesis is a research hypothesis. Okay, so we actually want to know whether or not we want to prove that, okay, we think this is already greater than 1.8, but the historical data says it's less equal than 1.8. Okay, so we want to support average data use is now more than 1.8 gigabyte per month. So we put this here. So when we reject the null hypothesis, that means the alternative hypothesis is true. Okay, on the other hand, this is the opposite, right? Mu greater equal than 1.8. So it will be someone saying that, okay, the assumption is the data use has gone, they want to say the data usage has gone down. So the null hypothesis will be the data usage is greater equal than 1.8. Okay, and if we reject this, that means yes, the data usage is less than 1.8. Or sometimes people will just say, I think this data is outdated. They don't have some expectation. They just think, I don't think this is the correct number. So the assumption will be mu equal to 1.8. The average data usage is 1.8 gigabyte every month. But if we reject it, that means, oh, it's not equal to 1.8 anymore. So that's why we have different, with almost this, when we do this, we do the same hypothesis test. But because of how we put different hypotheses, the interpretation will be different, even when we are doing the same calculation in statistics. So we have the two-tail hypothesis. Okay, two-tail hypothesis when the alternative is unequal to some number. Okay, so that means we assume that mu equal to 1.8 unless the sample mean is much higher or much lower. So this is both sides. So it's two-tail. Okay. So if it's within the confidence range, then we don't reject this. Okay, that means this is not true. The mu is equal to 1.8. But if it's in this, the yellow range, then we will reject the null hypothesis, and then we say, okay, yes, the average data usage is definitely not 1.8. And then for one tail test will be looking like this. So for the one that believe that the data usage has gone up, so they want to reject this, okay? So it means if mu is greater than 1.8, which in this area, then we reject. But if it's here, then we do not reject. On the other hand, if it's a lower tail test, if it's mu less than 1.8 here, then we reject the null hypothesis. Otherwise, we don't reject if it's here. Okay? So, what's the difference? The difference is this area. You know, when you compare two tails with one tails, right? So two tails, if this area is the same, the confidence level is smaller. So when we have two tail and one tail, depends on our confidence level, our alpha will be different, okay? So we can never say we accept the null hypothesis. We just either reject or fail to reject the null hypothesis, okay? That's the tricky part in the hypothesis test. So I think we kind of talk about this. So when we have, let me change the pen because I don't want it to. So when we have, remember we say, when we have this level, this is the alpha. Okay, alpha is the arrow. Okay. Oops. So alpha is the significance level, and that's what we call the type 1 error. So type 1 error happens is when the null hypothesis is rejected when it's true. So that means if there's error, like if the value we saw is here, but it's actually within the range, acceptable range, but we reject the null hypothesis, okay? So that's the type 1 error that's here. And then type 2 error is we didn't reject when it's not true because what we test is in this range, okay? So that's the type 2 error, and that's known as beta. So you see, if we want to make alpha, the type 1 error smaller, okay, then the beta will be bigger. But if we want to make beta smaller, then alpha will be bigger. So, you know, there's a fine line where, you know, we need to find a good balance. So this is like when we discussed, so when someone is, when someone committed a crime, but he was, what is it? He got the verdict of not guilty. Or when someone didn't commit a crime and then he was sentenced as guilty. Okay, so which error is worse? It's not, you know, it's not, I don't think it's not a comparable thing. Okay, so it's similar to what we say the type 1 error or type 2 error. And we don't want either, but it will just happen in reality, in statistics. So, but because of that, you know, usually we usually try to control the type 1 error to around 5%. Okay, so the type 2, this will be 95%. So usually that's what people do. So if we have the same sample size, reduced value of alpha will result in increase of value beta. Okay, and then or the opposite, alpha, when alpha increase, beta will go down. So the only way to reduce both alpha and beta is to increase the sample size. Okay, so let's do this one. So you will feel, oh, it's so similar to the previous chapter. So hypothesis testing when alpha is known. So when alpha is known, sample size is small, less than 30, then there's an assumption we must say that this follows normal distribution, then we can use whatever we are going to use. If the sample size is large, the central limit theorem says that, well, if it's large enough, more than 30, then in theory, it should follow the normal distribution. Okay, so we don't have to worry about, using different, though we can just use z-score. Okay, so examples of one-tail test. So this manufacturer mentioned that average life of a light bulb smaller than or equal to 8,000 hours. So suppose average life of random sample 36 of new light bulb is 8120 hours. So what's the population standard deviation? Assuming the population standard deviation is 500 hours. So what do we do? What kind of how do we do the one-tail hypothesis? Okay, so we could do both ways. Okay, so when we do confidence interval, we were given the z-score, right? And then we can calculate margin of error, and then we have the confidence interval. So what we do is we calculate the confidence interval and then see whether or not the range, the x, in this case, 8120. See this one, if this is within the range, okay? This is a confidence level approach. Or we can convert the 8120, okay? We can convert 8120. Oh my God, I'm horrible at drawing. Okay, let me change the pen. So we convert, let me draw the distribution. So the average is 8,000, right? And then we can do 8120. So we want to convert this to Z, okay? So that means 8120 minus 8,000 divided by the standard error of the mean, okay? So, let me delete this. So the first critical Z value. So to calculate critical Z, we have to convert the 8120 to, to the standard deviation. How many standard deviation is that? Okay, but the new hypothesis will be the average light bulb is less equal than 8,000 hours, but we claim it will last longer than 8,000 hours. Okay, so it's a one-tail test. So the value for the significant level, this one alpha, we choose 0.5. Okay, usually it's 0.05, 95% or 90%. Okay, so in this case, we want to do 0.5. And because it's one tail, that means when we are setting this to be 0.05, the 5%, this area is 95%. Okay, so to calculate the critical Z, so we have to look up the z-score. Okay, so the z-score here, when the alpha is 5%, okay, it's 1.645. So this number is the same as what is it? When we have two tails. Okay, so when we have two tails, I can draw this. Let me see if I can. Oh well, let's just do this for now, okay? So when I go back to class in person, I'll show you. I'll show you the table, and then we can see that. So 1.645. Okay, so this is one tail. So for one tail, alpha equal to 0.05, the z is equal to 1.645. Okay, so what's next? So when we have the alpha, this is 1.645, and we want to convert 8120 to this average with the same standard deviation. Okay, so x bar minus 8,000, the mu, divided by standard deviation, divided by the sample size, I think 36. Okay, so this is 8120 minus 8,000 divided by 500 divided by 6. So we have 120 divided by 83.33. So z is 1.44. Okay, so if you go back here, 1.44 will be here. So it's in the area where we don't reject the null hypothesis. Okay, so that means that, so this means even though our x is 8120, okay, it's 8120, but it's bigger than the average, right? But in statistics, so even though it's bigger, but it's not statistically significant enough. Okay, it's not in a 95% confidence level. So in this case, we can't reject the null hypothesis. Okay. So it's not greater than this. So we do not reject the null hypothesis. Okay. So that's it. So it shows here. Yeah. So we can't reject the null hypothesis. So that means that according to the sample of 36 new light bulb, we don't have enough evidence to reject the claim that the average life of the light bulb is smaller than or equal to 8,000 hours. Yeah. And then we have a confidence level approach. So it's very similar to what we did in the previous chapter. Okay, so the same thing, the null hypothesis is the average light bulb is less equal than 8,000 hours, but we actually think, oh, it's greater. Okay, so we will say, okay, we still use the same alpha level 0.05. And then we will convert the critical, we will use the critical z-score to calculate the confidence interval. So in this side, we only have one tail, okay? So we will only calculate the upper limit of that one tail. So in this case, it will be 8,000 plus 1.645 times the standard, what is it? The margin of error, no, the standard of error, okay, 500 divided by 6, so it's 83 point something. So it's 8137. So when you look at this, the x bar should be 8136.1. Anything greater than that will be significant enough to reject the null hypothesis. They will show us that, okay, we actually can reject the null hypothesis. That means we support argument that the light bulb life is actually now greater than 8,000 hours. But unfortunately, our x bar is here, so we do not reject the null hypothesis. So there's not enough evidence to claim that the average light bulb is smaller than or equal to 8,000 hours. Okay, So this one, this one, do I have answer? Oh, I don't have answer. Okay, let me just write it. Let me just do this here. So this one, the mu is greater equal than 50, and then the null hypothesis is mu greater equal than 50, and mu is less than 50. Okay, so this is also one tail. So it's here, 50, right? So if it's here, we reject. So the mean is 52. Wait. Yeah. 52. So we will calculate whether or not the difference is big enough, and then if we need to reject it, right? So 50 minus 52, negative 52, divided by 12, divided by square root of 36, which is 6. So this is 2. So negative 2 divided by 2, z-score is negative 1. And we know when we have one tail, we want it to be 1.645, right? So negative 1.645 is here, and then 1 will be here. So it's in the range where we do not reject, okay? So in this case, we can reject the null hypothesis. And then, therefore, we have to accept the nu is equal or greater equal to 50. Yeah. So any questions? So I think this is it. Okay. So this is what we well, let me see if I should. Yeah, I'll go over this really quick. So this is two tail. So we'll do two tail next time. Okay. So and then I'll show you. I'll pull out the table to show you the difference in two tail and one tail. Two tails and one tail. Okay. So this is for chapter 9. Thank you. Bye.